All right. So let me, very quickly summarize where we were at last time. So we started by, taking the momentum space modes. We split it into what we call sort of fast modes that lived in a small shell around, centered around k equal to 0. And then we were looking for sort of what the action is or the effective action is for these slow degrees of freedom, right? And what we did was we did this within perturbation theory in the nonlinear interaction. Okay. And we did this to leading order, although we said that there is a proper sort of cumulant expansion for this. For this effective action, we computed the leading order term here, right? So what did we find? We found that the effective action for the slow modes to leading order in U was given by the following. So let me just write down the term that we had. So we had the old, so this Q running to lambda by B. Actually, let me do this after doing the rescaling. Okay. So after doing the rescaling, we end up with something where we get T times B square from the first term. Then the second term was 1/2 kappa times Q square. And the third term had a coefficient which was U times B to the power of 4 minus D. This, remember, came from what we computed earlier. And then times 2n plus 4. And this, I said, came from the fact that there were two different types of terms, some of which had, where the way these alphas or this indices, the spin indices matched up, it gave us a factor of 2n plus 4. So there were 6 in some sense terms. The two types of terms gave us this 2n, and the remaining 4 just gave us a factor of 4. Okay. And then we had the term here, which let me write this as G times delta L. And this is the action that we had to leading order. And then there were terms which involved, so this just multiplies, the low energy fields after rescaling. So I'm kind of denoting it by the same phi as before. But these are the slow fields now that live within the shell, and we've just rescaled the momentum to get back the old cut. This is fine. Okay. And then we had the terms that were still left over, which, plus, order U square that we're going to compute today. Okay. But from here, we kind of figured out what the flow equations are. In other words, how do these parameters change? And let me write out sort of explicitly what this coefficient G was. So G was a momentum integral that ran over this little shell. So it kind of, we were integrating out all the modes in that little shell. And this had a factor which was 1 over T plus kappa times Q square that came from doing a certain Gaussian integral. And this is the integration factor that we have. Okay. So this, we can simplify this quantity. You can split this into, this only depends on the radial component. So we can split this into an angular and radial integral. Okay. The angular integral is going to give us a factor of the solid angle divided by 2 pi to the power of d. Right. So there was a ddq over 2 pi to the d, so that just comes along here. And now we have to do an integral over the radial component of this, which is just dq divided by times q to the d minus 1 divided by t plus K times Q. So we didn't explicitly calculate this last time. Okay. And so here you find that this integral is easy to compute simply because this shell is extremely thin, right? And so the function hardly varies over this little window. Everything is kind of smooth. And so in fact, you can replace this by just the solid angle over 2 pi to the d times just the value of the function here, which is lambda to the d minus 1 divided by t plus k times the stiffness, sorry, I didn't kappa times lambda square times the, with these integration limits, you get a factor of lambda times 1 minus 1 by 3. Right? And this, so we can sort of explicitly write out now, and this is what we did last time, is to say that, well, there is some half t here, and we wrote down how t is getting modified. So there's a part of it that gets modified simply by this factor, and there's a part of it, this is a q independent part. So we can sort of club these two together, and we wrote down the equations for how u change, how this t changes last time, right? So let me do that here. So this quantity here is this term in brackets is simply the little delta L, the little thin slice was lambda times delta L. So that little delta L is this quantity here. Okay. And so with this, we wrote down sort of what the equations were for these different things. So let's write out these flow equations. Again, so we had that this quantity was 2t plus 4 times u times g times n plus 2. So this was 1. And then the second equation we got was from recognizing that, after all this, there are terms that just involve, there are terms which just involve the slow modes. So let me kind of write out integral over q. Let me just call it 5. Okay, it's after rescaling and all of that. So you're left with this quantity. Right? So this gave us a factor of 4 minus d times u. And then dh, dl, we could read off simply by saying that, it's always slow. And we just had to take into account this rescaling factor. So that gave us a 1 plus d by 2 times. And what we were speculating was that, even though this looks like that fixed point that we started with at, so in the h equal to 0 plane. So let's say I have fine-tuned my magnetic field to 0. So I'm sitting at the fixed point for the field. We said that, in fact, there is no fixed point for t and u that is stable along any direction, right? And so we said that, oh, in fact, if I call this t and this is u, then in fact, this becomes unstable in all directions. Okay. And we thought that we could fix this problem by going to second order in this perturbation, which was controlled provided 4 minus d was much smaller than 1. So in other words, we'll assume here that d is 4 minus some small number epsilon. Okay. So of course, in the physical world, we want, we might want things like, epsilon equal to 1 or 2, corresponding to 3 dimensions or 2 dimensions. 1D, we already saw that there is no long range order, right? So the physical world, we might be interested in this, but really we can kind of think of epsilon as just some tuning parameter for now. Is this fine? Yeah, okay. So what we want to do today is to say, well, let's try and push this to higher order. But before doing that, it's useful to kind of read off these results using a diagrammatic kind of picture. Okay. So the idea here is that we'll kind of represent, things that are, quadratic in phi in the problem by having something like a line here that says, oh, that's kind of associated with sort of terms that are quadratic in phi. Whereas terms that are fourth order in phi, we can kind of represent by saying that, there are four fields that kind of meet at this point. And we have to ensure momentum conservation. So the sum of sort of momenta leading in here is basically going to be 0. So this is going to be our quadratic term. And this is going to be our nonlinear interaction. And we will assign labels or indices to this that correspond to these spin labels alpha, which I omitted here, but there is some alpha. There are some spin labels that we had. Sorry, there's also over some 3 different momenta. And we can assign spin labels. So these, in this quadratic case, both the spin labels are alpha. In the quartic case, 2 of them are alpha and 2 of them are some other index beta. So I can independently, I have to sum over alpha and beta independently in here. Right. So a quick way to kind of read off the effect of this first order correction that we found here in U is to kind of ask, well, if I were to kind of divide up this problem into slow and fast modes, then we would say, oh, well, I have something like this. I have a slow fields, right? Or I have fast fields for the quadratic part. And those just split up because we could really rewrite it as slow, slow plus fast, fast. There was no mixing between them. So this just splits into in this fashion. When we come here, we are no longer allowed to split it into slow and fast being independent. But there are various terms. So you could have, for instance, terms which are of the form where all of them are slow fields. And that was the kind of term that we were keeping here. Right. Then there were terms which involved, 1 fast and 3 slow fields, and I'm not putting those alpha beta labels here. Okay. Then we had things which involved 2 fast and 2 slow fields, or we could have 3 fast and 1 slow, or we could have all of them being fast. So these were the different vertices you could have got from expanding out this fourth order term. Okay. And I've clubbed a bunch of them together in kind of drawing this because I've not put all the alpha beta labels. Okay. So this one we are going to keep, and in fact, that's the one that we have here. Right. This one involves all the modes that are fast. So if we integrate over them, they basically drop out of the effective action for the low energy fields. So there's no need to keep them. They will contribute to the partition function, but they don't contribute to the low energy effective field. So this we can omit. It's not necessary. Right? And when we calculated to leading order, we said that, well, what I have to calculate are expectation values of terms like this. And we said anything that involves an odd number of fast fields will not contribute. Right? So this also does not contribute. And then we were left with sort of asking what is the contribution of terms like this when I integrate out the fast fields in the problem. Okay. And so to do this, we can kind of diagrammatically kind of see that integration over here just amounts to sort of calculating a certain expectation value of the form where we had this phi, sorry. We were calculating expectation values of this sort and integrating over them. So let's call that some Q prime. And we were integrating over Q prime when we did this calculation. In the full leading order cumulant expansion was calculating a function of the sort. This really amounts to then, taking a diagram that's of the sort. and saying that, I'm going to compute a certain quantity where this momentum and these momentum labels are summing to 0. And then this is an independent momentum Q prime, which is over the fast fields. And I have to now do this integral that amounts to doing this particular expectation value, calculating this expectation value. Is this fine? This is just a diagrammatic representation of what we did before. But this now I have to be careful when I do this, because now I have to put back kind of these alpha, beta, sorry. Sorry? Yeah. Correct, correct. Oh, sorry. So the effective action was that we said, well, my Z was some Z fast times e to the minus S effective for the slope. Yeah. And I have to integrate. Sorry, I still have to integrate over the slow fields. No, I'm saying by computing the correlation, how do you get you don't get the x1 by okay. Yeah. So what we did last time was to say, well, I can sort of compute my action was e to the minus S u, right? This involved both slow and fast field, right? And we had to take the expectation value of this with respect to the fast fields. Sorry, this is the 0, the non-interacting, right? With respect to the fast fields which have no interaction. So the free fast fields were what we were doing this expectation value with respect to, right? And that to leading order, we said is approximately e to the minus SSF u to, right? And so this is the quantity that we are calculating that gives us, the expectation value of this nonlinear interaction, but taken only with respect to the fast fields, non-interacting fast fields. Is this fine? Maybe I skipped a step from what we did last time. Is this fine? Do people have questions? Okay. So to leading order, then this SU, I can just replace it by its average value. So that's like when you do first order perturbation theory in quantum mechanics, you just take your unperturbed wave function and take expectation value. So it's kind of similar to that in this case. So now I have to do, so I can recognize that this loop is precisely this integral that we're trying to compute here. The value of this expectation value of this is the Gaussian expectation value taken in the fast fields. At 0 is precisely this 1 over TQ square integrated over the momentum window of the fast fields. Okay. All right. So this, then we have to say, well, I have to be a little careful because, I had this alpha, beta labels. So I should really be a little bit careful when I do this. So we would say, well, I can assign. So let's say this is alpha and that is beta. Okay. Then I could pick these two to be slow, or these two to be slow, or these two to be slow, these two to be slow. So there are many ways in which I can pick the slow fields in the problem, and I have to integrate over the remaining fast fields. And so you can pick this in several ways. So I could pick, for example, these to be the fast fields and these two to be slow, right? Or I could pick these two to be fast fields and these two to be slow fields. And similarly, the other type of combinations where I could pick these two to be fast and these two to be slow. This is alpha. And there are many ways to do this, how I could pick these two, or, I can pick it in many different ways, right? So you have to ask, well, if I pick it in this fashion, then I'm kind of integrating over these fast fields, right? That's what this was, okay? If I'm picking this one, I'm kind of doing this integration. If I pick this, I'm doing this integration. Okay. But each of this gives us a different factor, because this one, when I do the summation, I end up with phi alpha for the slow fields, and that is fine. That's what I end up with here. Okay. But the sum over beta is like a free summation that I have to do now, and I can sum over them completely, right? And so this gives me a factor of n associated with the sum over these beta, right? Similarly here, I have an arbitrary sum over alpha, and so that's going to give me a factor of n. Okay. And now there are 4 different ways of choosing, out of these 4, I want to choose, I could choose this to be alpha beta, or this to be alpha beta, or the other way around, I choose alpha beta and alpha beta. So there are 4 of these terms that appear, but these will constrain alpha and beta to be equal when I take this expectation value. Remember that this quantity here, if I had an alpha and a beta, this quantity was proportional to a Kronecker delta, aside from 1 over t plus kq square. It had a Kronecker delta over alpha and beta. So that's going to force these 2 indices to be the same. And so it's going to force these 2 indices to be the same, but there's no sum on alpha that's left over n. Okay, so these do not carry factors of n. So adding these together gives us sort of this factor of 2n plus. Okay. There are 2 terms with n, and there are 4 terms that don't carry this factor of n. Okay. Okay. So this is a simple kind of way to then reproduce the leading order correction. The factor of u comes from the fact that each of these nonlinear interaction carries kind of a factor of u along with it. And the momentum integrals that you have to do here give us a factor associated with 1 over u. So this side, this 2 pi to the d, some delta function of, so imagine this was q prime and q double prime, some delta function of q prime plus q double prime divided by t plus k. Right, so we had everything here come from doing this calculating this. All right. So now with that, with that in mind, yeah, sorry. Correct, which we will compute. Right now, we didn't keep it. Last time, we didn't keep it. So we're going to do it now. Yeah, correct. Okay. So I'm going to erase this, and then we will just write out, but I'm going to, just in the interest of time, I'm going to kind of do this in this language of diagrams without worrying about sort of, how I'm precisely doing the calculation, but you should, so this involves something called Wick's theorem, which I'm not going to derive, okay? But it involves the following, which is I want to ask, well, if I go to next order, right? I want to go to u square, but u square has 8 of these fields now, right? And so I want to compute something like phi, and I have another factor of this at order u squared, right? 4 of these I'm going to assign as slow. So let's say, I'm going to just pick some of these as slow, some of these as fast, right? All the slow fields, I'm not doing this averaging. This averaging is only over the fast fields, right? Which means I still have to do something like u square times I still have to do this averaging. And Wick's theorem is a statement about how to compute averages of the sort in a free theory or a Gaussian theory. It just says that the way I should do this is to take pairs of these and write it as a product of this expectation value times this one, or this expectation value times that one. So take all possible pairs of these, pair them up, and the answer is going to be a product of, correlators of this sort. Okay, so I'm not going to derive it, but from here, we can kind of write out what the diagrams are for this problem. Okay, and in the interest of, what we did last time was to recognize that, this physics is pretty much not going to change. because this is the momentum mode at q equal to 0, and that's going to survive unaffected, right? This here, we said, well, I have calculated that this quantity here, t plus u, I have calculated it to some order, right? And now we wanted to kind of ask, imagine you wanted a fixed point, right? We just want to keep all terms that are of the same order in the problem. And so we said, if there is a fixed point here because of some term like some gamma times, sorry, I'm using all these exponent notation, but these are not, I mean, these are just some coefficients. Yeah, something times u square, you might expect if you go to higher order. And we then said that, oh, if this had to have a fixed point, it would happen at a value of u star that is of the order of epsilon, right? So 4 minus d was epsilon. And we assume that epsilon is small. Right? If epsilon is small, then this quantity gives me a, if I don't have this, then u just flows off to infinity. That's what this picture was, right? But if we have a term that has a second order in u correction, then we expect that I can have a fixed point here, right? But the fixed point will happen at a value of u that is proportional to epsilon, right? So just to be consistent, if I have something which is of order epsilon times epsilon, then this will be of order epsilon square. So it's kind of consistent that these two are of the same order. They can compete, right? Here, on the other hand, you would expect if u is of order epsilon based on this, right? Then this one here would also be of order epsilon in order to get a fixed point, okay? And then in particular, I don't have to go to order u square corrections here because those are higher order compared to me. Okay, so what we really want is just this correction to this one term here in order to stabilize a new fixed point if it is possible. Is that fine? Okay, so what we're going to do is kind of, it's a bit of a fudge, but I'm going to assume that these diagram-like rules that we write down actually make sense, which one has to actually check carefully by doing the calculation explicitly. But what we said was, if we want to go to second order in this, right? Right. So remember that we wrote down this thing explicitly to two orders with slow fast. We said that this was approximately e to the minus s. This we already calculated, but we wrote out what the second term was, and the second term was the second cumulant, which is like a, the standard deviation of this operator, right, or this action. So it's the average of the square minus the square of the average. That's the second cumulant that you're going to get from this calculation. So what we're really going to compute is this quantity. And I'm going to ignore all higher order terms. So what is the second order? You see that there are a few things that we can read off. So first of all, in the second order action, you have a factor of minus 1/2. Okay. The minus 1/2 reflects the fact that you've gone to second order. Otherwise, there's nothing special about this factor. It doesn't involve doing any calculation. This one is going to give us a factor of u square. I mean, each of them goes as u square. Okay. And now we have to sort of calculate this quantity, which involves doing a calculation of this, except we have to subtract off the mean square, the square of the mean. Okay, and what that amounts to is to kind of diagrammatically amounts to taking diagrams of the following form, where maybe let me erase this. Actually, let me erase this here. We'll just modify this equation in a second. Let me erase this one here. And so now we have to write out sort of the diagrams that would contribute to this order. Okay, so let me kind of draw those here. You would say, well, if I have order U square, I have two of these interaction vertices, each of them carries a factor of U. Okay. And now one of the things about subtracting off the square of the average, and again, this is not something that I'll do right now, is that the only diagrams that I need to worry about are those which are completely, which are connected diagrams. In other words, I can't assign all of these as fast and all of these as slow, because that will not contribute when I subtract off the square of the average. Okay. So our assignment is going to be such that the slow and fast fields have to be assigned such that we are looking for something which contributes to the interaction. It has to contribute here. So the specific contribution we are looking for is, connected diagrams where there'll be fast fields from both of these that I can sort of connect. And they have to have 4 slow and 4 fast, because I want to be left with 4 slow fields that will contribute to this correction, right? So the way you would kind of do this is then, you can kind of write out diagrams where you pick sort of 2 slow fields from one and 2 slow fields from the other. And the diagram that you want to compute is basically going to be a calculation of this quantity. Okay. So this would be the connected contributing to 5. So now we have to kind of do this again. So let's kind of do this by first kind of writing out labels. Okay. So let's write out labels, and then we're going to kind of connect them up. So let's write out labels. I say, oh, well, let's say this is alpha, this is beta, and this is some mu and nu. And now I have to assign, I have to pick 2 of these as fast and 2 of them as slow. Okay. And now I have to connect the fast fields together. Okay. So let's kind of do this counting that we did in this case. So you'd say, well, the way I can assign is I can assign these 2 fields to be fast fields, which have the same index beta. I can assign them to be fast. I could assign 2 of these also equal ones to be fast fields. Okay. And now if I do this integration, you would say, well, this is beta. If I now connect it up in this fashion, right, then this beta will become equal to mu because of the delta function, the Kronecker delta. This beta is equal to mu, but I am left with 1 free sum over beta, okay, or over mu, whichever, right? So you're left with 1 free sum. So things like this will contribute a factor of n, right? And I just have to count, how many of these types of diagrams there are that will survive in the end, right? So the way you do this is to say, well, I have 2 ways of picking the fast fields. I could have picked these 2 or these 2, right? So that gives me a factor of 2. Okay. Similarly, I could have picked either these 2 or those 2 from the second one. So that gives me another factor of 2. Okay. And now I have to kind of figure out, once I pick that these are the fast fields, I have to figure out how to connect them together. And I could take this line and kind of connect it up here, or take this line and connect it up here. Okay. And so that corresponds in this Wick theorem to different ways of pairing the fast fields that I was talking about. Right. So this one is going to give me sort of yet another factor of 2 from that choice. Okay. So this comes from kind of picking on vertex 1, picking on vertex 2, and this comes from kind of actually picking how to connect them together, right? And each of those choices is going to give me a factor of n. Okay. And here I'm going to be left with sort of alpha and nu as slow fields, and that's fine. There are two alphas and two nus. So it'll give me a term of the nonlinear term that we had of the same sort that we had. Okay, so this is kind of one type of contribution. Okay. A second type of contribution could be that, I pick the fast and slow fields to come such that, maybe they are not the same index, right? But it could be such that they are not the same index on one, but they are the same index in the other, right? So we can pick something of the following sort where I have beta. I could pick this one to be fast, such that one of them is alpha, one of them is beta. And then in the second one, we still pick the fast fields in the way we did here, right? So we could pick the fast fields the way we did here. And now we can ask, well, what are the types of contributions you're going to get? So you want to sort of connect up this one here, and you want to connect up this one there. You still are left with two lines hitting this vertex. So it looks similar to this picture here that we drew here, right? Except these labels are now different from the ones that we have. Okay. So what are we going to get from here? We are going to get that beta has to be equal to mu. Alpha has also got to be equal to mu, right? So this says that alpha, these alpha, beta, mu are not independent anymore, okay? But you get one free variable. So if I fix alpha, right? So the slow field, if I fix alpha, then alpha becomes mu here, right? But mu becomes beta, okay? So I don't have any free index that I can basically sum over in this particular case. So there's no factor of n because there is no free index that I can sum over for the fast fields, right? So these are all the fast fields in the problem. So you see that, oh, there can be no factors of n associated with diagrams of this sort. The only thing I can do is I can sort of count how many ways there are, right? So here I want to assign, two of these to be equal. So we say there are two ways. So let's count. Okay, I'm counting on the right first here. So let's count that there are two ways of picking the two indices to be equal. I could have picked these two or those two. So there's a factor of 2. Okay. On the other hand, here, I would say, well, I could have picked alpha not equal to beta. So I could have picked, any of the 4 possible choices in this case, right? I could have picked alpha, beta, or alpha, beta, alpha, beta, alpha, beta. So I could have picked 4 out of the many possibilities would work, right? And once I pick these two, I have to say, well, mu could either connect to alpha or mu could have connected to beta. So there's a factor of 2 associated with this. Okay. And this is almost correct, except that we didn't kind of figure out which of these 2 vertices we wanted to assign the 2 fast fields to be unequal, right? So we said the 2 fast are alpha and beta to be different, but I could equally well have done that on the second one. Okay. So there's an additional factor of 2 associated with kind of making that choice. Okay. So this gives us a factor of 832. So this gives us a factor of 8n. This gives us a factor of 3. And we have one more. I'm just going to erase this one here and write out the third option. So what is the third option? The third option is we make this unequal choice on both of them, on this vertex and that vertex. So this would correspond to taking, so let's say this is alpha, alpha. And now I'm going to pick, let's say, these as fast fields, not the same index as fast fields. Similarly, here I'm going to pick not the same index as fast fields. Okay. And now I can sort of connect them up and kind of do this integration. And again, you're left with two incoming lines, some bubble type in between, and then two outgoing lines. Right. So the form of the end result is very similar. Okay. Again, here, once you fix alpha, you would say that, oh, well, alpha gets fixed to mu. Okay. Similarly, beta gets fixed to nu. In fact, you don't have any degrees of freedom left at the end of the day. Right. So there's no factor of n associated with this. But now the counting is going to be a bit different. So here I've chosen both of them to be unequal index vertices. So here I have 4 ways of picking, alpha and beta here, right? Similarly, I have 4 ways of picking mu nu. So I have a factor of 4 times 4 coming from those choices. Okay. And then when I'm connecting them, I can either connect this alpha to mu, or I could have connected alpha and nu together. Okay. And so that gives us sort of an additional factor. Okay. So this again comes from the choice, this comes from the choice, and this comes from sort of how to connect them. Here we didn't explicitly write out, but you can kind of write out the counting where this came from. Okay. So this gives us a factor of 32. So with that, I'm going to write down sort of this. And again, these are things that, one has to actually work out that this is the right way to do the calculation, right? But I'm kind of, in the interest of time, I'm kind of skipping steps and just writing it with diagrams just to get to the point. Okay. So here, what are we going to get? We are going to get this minus 1/2 u squared just came from here. Okay. We know that we are going to get slow fields, 4 slow fields at the end of the day when we do this calculation. Okay. These 4 slow fields will satisfy, momentum conservation. So you'll get Q1, Q2, Q3 with momentum conservation. All these momenta will run only to lambda by b, right? So this will be kind of the slow fields that you're going to be left with, and it will be of the form some alpha alpha. Yeah, sorry. Yeah, yeah. There's just one component. Yeah. Yeah. N is 1 for the Ising case. Yeah. No, so they will all contribute. All of these will contribute in the case where the Ising case is n equal to 1, but I have to add up all of them. Dominating. Well, they all give the exact same contribution, right? It's the contribution associated with that one. Correct. So each of these comes with a factor of u. So this is everything to order u square. And all the momentum integrals will be of the form that we'll write out in a second. Okay. So now we come to a bit of this thing, which is to say, well, I have momentum conservation that I'm going to satisfy. Okay. But what is momentum conservation going to look like? I'll have 2 momenta here. Okay. And I have 2 momenta there. And I have momenta here that I have to integrate over, right? So in general, you would say, well, this vertex doesn't quite look like the one that I started with, because in general, I would have had, this is going to contribute like the following, where, I would, let's say, draw something of this sort, right? I would say, well, I have some Q1, I have some Q2, and in general, there can be some Q3 and Q4, let's say. We know that this 4th one must be minus of 1 plus 2 plus 3. So this is going to be minus Q1, minus Q2, minus Q3. Right. When I come here, you'd say, well, I could have had some Q4, Q5, or let me call this something else. Q12. Okay. And I could have had some Q3 and Q4. And I have to satisfy momentum conservation. So eventually 1, 2, 3, 4 will all add to 0. Okay. So this is going to be. But now you kind of see that there is a problem with this, because now my answer is actually the answer to this integral is going to explicitly depend on, these momenta that are entering in the problem. Right? So it explicitly is a function of, for example, here it's explicitly a function of Q1 and Q2. Okay. So you would say, well, this doesn't quite look like a constant, right? It looks like something where I called it like a vertex, which was a number, right? But here, that thing could actually become a momentum dependent function, right? So the more general thing here is that this is not of the form U square. It's of the form, I'll have some, some Q1, Q2, Q3, -1, -2, -3. And in general, I'll get some not, it'll be U square because it's some, there is a number associated with each of these. But when I do this integration, I would get some function of Q1, Q2, Q3. In general, there'll be some function here. So it'll be a momentum dependent kind of interaction, although I started with something that was momentum independent and completely constant, just a constant. Right? And so now we have to kind of make one additional assumption, which is that, if we encounter interactions of the sort, we are going to assume that all these are slow fields. They have momenta which are very small. Okay. And now I can kind of Taylor expand this vertex in powers of the momentum as well. Okay. So we're going to make the assumption that the leading order correction that I want is going to be obtained by setting all of these external momenta to be precisely 0. And the only thing that I then want is a very specific integral over the fast fields here, which is going to be one of them with Q, one of them with minus. Okay. So there's one additional assumption, which is that the interaction in general, this vertex is going to become non-local in space. Okay. But we are going to assume that at small momentum, I can Taylor expand whatever function that I get here for this momentum dependent vertex and replace it by something that's just a constant. So I can Taylor expand whatever I get, and the value of this, which we'll calculate in a second, by setting all the external momenta to be precisely 0. Yeah, sorry. Correct. 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 Mm-hmm. Yeah, so you have to be okay. So let's come to a different point. Let me kind of mention one thing, and then we'll go back to this calculation, which is that exactly what Dibendra was saying, namely that this assumption that I get something momentum independent will of course break down if I have more points in momentum space where the fields are like slow fields, right? So a simple example of that is what I kind of drew when we started last time, namely, is it okay if I erase this? Okay. So we remember that when we started doing this coarse graining, we took the point of view that we are sort of trying in momentum space to zoom in towards momenta which are sort of where the critical degrees of freedom sit, right? And so for a ferromagnet, we said, oh, it kind of sits there, right? For an antiferromagnet, it sits there at pi, right? But I mentioned one case where you could have modes that sit at symmetry equivalent points. This point is the same as that point, and this is the same as that, right? It could sit at two inequivalent points, pi, 0 and 0, pi. in a lattice, on a square lattice, this kind of thing is allowed, right? And if this happens, you see that, I really have to worry now about, even though I might start with local interactions in real space, right? I would have to kind of allow for, what are the possible kinds of interactions, some of which could be that all the slow fields could be here, right? So you could get terms, so let's call this phi and psi. These are the two fields now, right? I could have something where all the slow fields come from in the vicinity of this momentum, right? So you could get terms of the sort phi, 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 right? You could also get terms of this sort, which are like psi, psi, which kind of look like, I've zoomed in towards this momentum and it looks kind of ferromagnetic. All the momentum transfers and so on are small, right? But you can also get interactions where, you take, two of these slow fields from one side and two of the fast fields from the other side, okay? And these are allowed because, if I write down this thing here, it's like involves momenta, which are two factors of pi, but 2 pi is the same as 0 on the lattice. Similarly here, 0 comma 2 pi, but 2 pi is the same as 0. So in fact, terms like this, if these momenta are, both close to pi 0, then individually, then this is like a slow momentum degree of freedom. Okay. If you look at complex fields, which we have not done here, but if you look at fields, I mean, I can write down the n equal to 2, as I said in the beginning, that you can think of like a 2-component magnet as a single complex bosonic field. And if we do that, then you can say, well, I want to be able to write down not just real fields here, but they will have indices, but I could equally well think in terms of complex fields living at each point. And so now you would say, well, in that case, imagine this, I do this for a complex field. You could get terms, of this sort, of course, but you can also get terms of this sort. And now this means that, I take two particles and I kind of scatter them from here to there, right? You could also get, processes where I take particles and scatter them from here to there, and another one scatters from there to here. Okay, if you have additional labels, you can kind of distinguish processes of that sort, and those will involve momentum transfers, which are, like pi pi. Okay, so it's not true that if you have multiple critical modes in your problem, okay, then in general you have to worry about the momentum dependence of this function. Okay, and the most kind of dramatic case is, imagine I give you a system, and this is not something that we're doing now, but imagine I give you a system of fermions where I have some Fermi surface. So now I'm kind of writing down a theory of fermions, which you've not done, but it's some problem where I can similarly write down interactions between fermions living at different momentum points. And now you would say, well, I can write down interactions between fermions at different points in momentum space. They can scatter off of each other. And in general, I have to keep track of this entire momentum dependence. And in fact, my RG must be done such that I'm kind of going towards this surface as my low energy space in the problem. I'm not coarse graining towards one special momentum or two special momentum points. I have to kind of coarse grain over something which I'm kind of zooming in towards an entire surface, or in d dimensions, there's some d minus 1 dimensional kind of space towards which I have to now coarse grain and go towards that in momentum space. Okay, and so this involves a more sort of complicated versions of renormalization, what people call sort of functional renormalization group processes. So I'm going to omit, we didn't discuss fermions at all, and I'm not going to do that, right? But just to answer Dibyendu's question, I mean, this is clearly, insufficient in cases where we have multiple modes that are important in the problem. So with that, let's kind of go back to this and ask, well, if I set all these external momenta to 0, then I'm only left with one integration that I have to do. Namely, I have to compute an integral over Q running from lambda by, so this Q twiddle running from lambda by b to lambda. And one of them is, this Green's function that we computed, which gave us 1 over t plus kq square. Square. The second one is the same one, but computed with minus q twiddle. Right? So this is going to involve exactly the same thing, except because q twiddle and minus q twiddle give me the same answer, this will be sort of just an exact one more factor. And this is also easy to calculate for the same reason, namely that the shell is so thin that nothing depends on momentum. This is a very slowly varying function of momentum. And so again, you can calculate this by writing it as a solid angle in d dimensions divided by 2 pi to the power of d. Times, I can compute these quantities directly on that shell, right? So this is going to be 1 over t plus k time, this kappa times lambda square whole square this time, because there's 2 of them, right? And other than that, I have this, lambda to the d minus 1 coming from the radial integral q to the d minus 1. And the dq gives me a factor of lambda times 1 minus 1 by 3. So what you get from here then is a factor that looks kind of very similar to what we had before. So this is some omega d divided by 2 pi to the d times lambda to the power of d. Here, so I'm just combining these two, divided by times 1 minus 1 by b, but that was just delta L. Is this fine? I mean, we've kind of skipped a number of steps, but oh, sorry. Times this factor. Okay, I erased that factor. Let me. Sorry, do people remember what that factor was? Sorry, say 8n plus 64. So I have all of that coming from the counting, this from calculating the data. So now we can kind of take this and feed it in here. Basically, what we've done is calculate effectively what the value of this gamma is. So what do we have? We have then this equation doesn't change. The first equation does not change. Everything we've calculated already to order epsilon here, right? So this is going to give us 2t. Sorry. Plus 2. And g here was, sorry, so I'll write down what let me call this G1. I'll write down what G1 and G2 are in a second, right? So this is G1, du dl was epsilon times u plus, let's write it as some minus of minus. Actually, let me just call this u times G1 for now. And we'll just write out what these G1, G2s are. Okay. And dH, dl to this order is just 1 plus d by 2. So G1 was this 4u times, 4 times n plus 2. And it had the factors of the solid angle divided by 2 pi to the d times this factor of lambda to the d, but 1 power of t plus k lambda square. And G2 was very similar. So it just had a factor of okay, so there's a half from here, and then there is this factor. So it's 8n plus 1/2 times let me just double check. This is fine. All right. So we have this form, okay? And now this, we can kind of start doing what we did before, right? So we can kind of draw what happens to this diagram, this flow diagram, okay? And ask what are the fixed points in the problem and what do we learn by kind of going to the vicinity of these fixed points, right? So you see from here that, there is certainly a fixed point if I just set t and u to be 0. So let's imagine I'm always in the h equal to 0 plane because this equation completely decouples from these two, right? So let's imagine that, the magnetic field is always relevant. It breaks the symmetry and it's going to kind of give you some ordering of the spin field, right? So this is always kind of a relevant perturbation. And we have to always tune this to 0 to get a phase transition, right? So let's imagine I have done that, right? So I've gone from some large space into sort of, let's say, the space of these two. And now you see that there is going to be a fixed point where u is positive and it's going to be of order epsilon divided by G2 here, right? So u is going to be positive. You're going to get some fixed point up here. But if u is positive, then you see that this t is going to be a fixed point which is at some negative value, right? So you're going to get a fixed point that sits here in addition to this fixed point at 0. And now we want to ask sort of, so we know what the fixed points are. So let's call this some u star, t star, u star. So this fixed point here, remember, was the fixed point that was, stable above 4 dimensions. So remember that above 4 dimensions, the flow was not like this. The flow was, so this is d less than 4. Okay. And in d greater than 4, remember that the flow was, of this sort. Where in fact this u was not important. And if you turned on a u and you tuned yourself to a certain temperature, then this u was actually not relevant. Okay. So the flow was kind of like this, where I could tune this one parameter and hit the critical point. Here, you would say that, oh, I have to tune both t and u, and that we said is unphysical for a ordinary critical point. Right? And what we find here is that when d is less than 4, certainly this becomes unstable. Okay, that's what we drew here. But we find that now there is a new fixed point, right? And now I have to ask, well, what do the flows look like when I kind of draw this flow in this entire space here? Okay, and it turns out the flows look like this, and this is something that needs some work because you have to go around this fixed point now and linearize these equations and ask, how the little change in temperature and u will take you away from this new point. Yeah. Sorry, and there is epsilon. Sorry. So here epsilon is 4 minus. Correct. And yeah. Yeah. And at this order, in fact, since everything here is already at order epsilon for these quantities, in fact, it is valid to this order to set d equal to 4 in the value of G1 and G2. Because if you keep, so you could take, omega d and try and expand it as omega 4 minus epsilon and Taylor expand this solid angle in powers of epsilon. Similarly, quantities like this, you could try and Taylor expand in powers of epsilon. All of those will give you higher order corrections. And we have not kept anything to higher order in epsilon. Okay, so to be consistent, we could kind of replace this by, just omega 4 and 2 pi to the d would just be 2 pi to this order. That's fine. All right. So what we find, if we kind of do this, you would have to say, well, I have to take into account now the change, if I go a little bit away from T star, U star, how do those little delta T's and delta U's flow as a function of the renormalization group process, right? So you would have to write down now a d by dl of delta T and delta U. Okay. And this will be some 2 by 2 matrix, and I'll write out the entries. Okay. And so linear order, it will be some linear matrix equation corresponding to this evolution. Okay. And as was already kind of pointed out, early on when we were discussing scaling, it's not necessary that delta T and delta U stay orthogonal degrees of freedom. So in fact, there are off-diagonal entries in this matrix so that the correct, eigenmodes are not necessarily, these axes that we've drawn here, right? The correct eigenmodes are going to be some linear combinations of delta T and delta. Okay, so let me just write out all the terms here. Okay. So delta U and delta T are going to be simple. Okay. And so let me write out sort of what these are. So this is 2 minus, and this is a little bit of work just to sit with this equation, linearize it around this fixed point. So let me actually write out both the fixed point and these equations. Okay, so this turns out to be 2 minus epsilon plus 2 over n plus 8. This one turns out to be some number, and I'll write out what this is to this order. And importantly, this number turns out to be to order epsilon, it's actually 0. So it's kind of is some number of order epsilon squared. Okay. So this, let me write out sort of everything that we need from here. So T star and U star, let me write out to leading order in epsilon. T star is some minus epsilon times k over 2 n plus 2 by 8 times lambda square. Okay. T star, sorry, this is T star. U star is epsilon times k kappa square over 4 times n plus 8 times, this quantity here, omega 4 by 2 pi to the 4. Oh, sorry, you can't read this. Let me just write it here. So, let me write it here. Is this okay? This is fine. I'm sorry. Okay, let me just write the whole thing here. Let me just erase this and write the equation. Yeah, so let me come to that in just one second. Okay, so let me write out sort of what these things are. So just give me 1 sec, then we'll. So T star was minus epsilon K divided by 2 times 8 times lambda square. Um, and so let me just write down this. This is of order epsilon square. Okay. Sorry, before I come to your thing. So the thing to note from here is that, we find a certain fixed point, and there's a little bit of rationale for kind of understanding at least, the position of this fixed point, right? At least heuristically, you would say, well, look, what interactions do is, in this case, they suppress the nature of the ordered phase. And crudely speaking, that's like saying, well, if I have something like 5 to the 4, right, then I can replace it by, in mean field theory, we replace this by something of this sort, right? And what this tells us is, even though I might have started with, some bare t, the original critical point would have happened when t flipped sign, right? But the interactions are giving me some positive shift to this t, right? So the new transition point should be at some negative value of this parameter, right? And to order epsilon, it's kind of happening at some negative value that's of order epsilon and set by the strength of the interaction u, right? So this is u. Right. So it's, and u itself at the fixed point is of order epsilon. So this thing is shifted to negative values with some order epsilon. Okay. So at least this position in temperature axis kind of makes sense. Okay. Okay. So the second thing is to kind of ask, well, what happens if you take a flow like this, right? Then you see that, in fact, you're going to mix the eigenmodes are going to be mixed. And in general, I will couple delta t and delta u. I mean, imagine this is also non-zero, right? Then in general, I will couple delta t and delta u. So I should be drawing sort of flow diagrams, not in this. I mean, I can use this, t and u coordinate system, but the flows are not going to be perpendicular or kind of along the axis that we've drawn there. Right? So the way the flows look is now going to be of the sort where this fixed point became unstable. Right? But you're going to get flows that look like this, where you're going to flow in this fashion. So you get flows that, I'm kind of just sketching it. So what you find is that, there is kind of line here where I can't say, well, I should tune u if I start off here, right? It's not that u flows to 0 or that u flows to this fixed point. But if I start somewhere in this space where, imagine I'm tuning temperature, but at some value of u that's not 0, right? And imagine I start off my couplings here, then I would end up, flowing to the large T value. So I'll end up going to the disordered phase or the paramagnetic phase. If I start off a little bit to the left of this line, I'm going to end up in a phase where my temperature is going to go to minus infinity. Right? So I'm going to end up in a phase which is deeply in the ordered phase. Right? But I can tune this one parameter and find a certain point just by tuning one parameter. I can find a certain point where I will flow into this fixed point here. Okay, so this tells us that this critical point is actually accessible by tuning one parameter. Okay, in this case, in the earlier case, we said, oh, if we did this naively, we would say, well, I ended up getting something that looked like this. So certainly this fixed point cannot be accessed by tuning one parameter. So it's not a critical point in the ordinary sense, right? H has to be set to 0, of course, right? But I cannot obtain it just by tuning temperature. I cannot reach this point, right? Here, on the other hand, this new fixed point that we find is in fact accessible by tuning one parameter. Okay, and so it's really the physics in the vicinity of this point that's going to dictate the physics in the vicinity of a real phase transition. Okay, not what is happening here, but rather what is happening in the vicinity of this point. Okay, and which is why it's important to know how these quantities, like the temperature or these parameters, how are they going to flow in the vicinity of this new point. Okay. So one thing you see is that, imagine I get extremely close to the critical point, right? So I'm kind of starting my microscopic, coupling somewhere very, very close to this point. Then I'm going to go very, very close to this fixed point here until eventually I realize that I'm slightly below TC and I'm going to sort of flow away. Okay. So if you do that, you would say, well, I can try and understand the behavior of exponents by really taking this parameter here and setting it close to 0. Right. So this is like an irrelevant coupling now. It's not going to grow under the renormalization. So it's corresponding. Remember, we had these, scale factors of b to the y. The y is going to be negative for this axis. Okay, it's not yu, it's some linear combination now of u and t, but this is some direction along which that is going to decrease. Okay, but you have one relevant parameter, which is yt, and we can read off sort of what that is by, basically we can forget about delta u now. Let's say I've renormalized such that delta u is close to 0, right? Then really this quantity is going to read off, is going to be my reading off of what yt is. Right? So this tells me how my temperature is going to renormalize when I am sitting very, very close to this critical point and I start doing my renormalization. Then this is going to give me something where yt is 2 minus epsilon n plus 2 divided. Okay. And from here, we can kind of read off what nu is, the correlation length exponent. And the correlation length exponent was just 1 over yt. And so to this order, this correlation length is a little bit bigger than a half. It is some epsilon times n plus. I'm just Taylor expanding this inverse of this in powers of epsilon. And so you find that very nicely, this value for nu does not care about the interactions at all. Okay, but it does care about dimensionality through epsilon, and it cares about the number of components of the order parameter. Okay, so what we find is doing this calculation, we kind of properly, we find that, we find a new fixed point. We find that, although this one gave me some bizarre answers, this one actually is a nice critical point. And at this nice critical point, the values of the exponents, which kind of dictate the behavior of the correlation length, we find that it does not care about the microscopic details. What is the value of t or what is the value of u in my microscopic Landau theory plays no role here. Instead, what it depends on are, basically numbers that tell me something about the symmetry of the problem and the dimensionality of the problem. Right? So what you find are, and we can write out all the other exponents. And they depend on two things, namely the symmetry of the problem. And in this case, the symmetry is encoded, in terms of number of components here, right? How many components is Ising symmetry or XY, Heisenberg, and dimension. And now let me just make a table for sort of what the various exponents are to this kind of order. And I'll kind of then turn to what Dibyendu was asking. So let me just write out, at least two of these exponents to leading order. And let's say I take d equal to 3. So epsilon is 1. And new computed, using this thing for n equal to 1, n equal to 2, and n equal to 3. They are all very close to each other. So this is like about 0.58. This is 0.6, and this is 0.61. So it doesn't depend sensitively on n, but it does depend on n. This is from the epsilon expansion, but setting epsilon equal to 1, which may or may not be justified, right? But that's what this is. And the values from numerics and experiments are kind of close to the following. And just to this thing, the mean field theory value was nu was 1/2, independent of dimension and independent of the value of n, right? So what this captures, at least in d equal to 3, is that there is in fact a systematic dependence on the number of components of the spin. So it does depend on the symmetry of the problem. And you can do this also in 2 dimensions for n equal to 1 for the Ising case. I haven't written down the numbers, but you can do that. Similarly, let's write out one more. So gamma for the same thing, it turns out to be 1.17. Again, this is within this epsilon expansion. Epsilon just naively set equal to 1. And the values from these are the numbers that you get from experiments and numerics are kind of closer to these values. Okay. So again, you see that there is a systematic dependence on the number of components. Although here you see that, okay, this one does a little bit, it seems to be getting worse here. When you look at, n equal to 3, it seems to be getting worse at this order. Okay, and all the other exponents you can kind of relate to these two as we discussed. We really said that there are two independent tuning, two independent exponents, what we called yt and yh earlier. And so those two numbers, you can basically, using these two exponents, all the other exponents you can read off. So I'm not writing them out explicitly. Yeah. Which parameter, what parameter are you talking about? Are you talking about the range of the interaction? Okay, so here we have only done this for short range. Correct, correct, correct. And I think somebody already asked a question earlier about what happens if you have long range interactions, and then you have to kind of redo this calculation more carefully, because it's possible that depending on what the precise, so there'll be some 1 over r to the power of some number, right? 1 over r to the sigma, let's say, governs the power law fall off of the interaction. Then depending on that power, maybe these exponents could depend on the value of that power, right? But we've only done this now for short range interactions. Right? So we would have to redo it for those cases. We have to read this carefully. Okay. So just to kind of, answer the Bindu's question. So if we do this, okay, I didn't write down values for epsilon equal to 2, which would be the 2D case. So you might in fact find that, there is, this gamma does, just as badly as this Migdal-Kadanoff RG. We said, oh, that's kind of ad hoc, right? And different ways of doing it, in fact, give us somewhat different answers, right? And you might say, well, even here it looks like this. I have done this to order epsilon, and it seems arbitrary to just set epsilon equal to 1 when I'm doing this expansion, assuming epsilon is small, right? So really, the power of this approach, is that if one extends this to higher orders in epsilon, people have found ways to actually estimate critical exponents, which are kind of get systematically better, if you kind of do this in a specific way, looking at higher orders in epsilon, okay, or effectively going to higher orders in perturbation theory itself. So not something that we are doing, but at least it's some statement that there is a way. In other words, there is a way to imagine systematically improving this calculation by saying that I'll calculate things to order epsilon square or epsilon cube. And in some cases, people have calculated this to fairly high orders in epsilon, right? And then one has to find a way of asking, does that series in epsilon converge? And if it doesn't converge, is it some kind of asymptotic series where I have to kind of find ways to either resum that, or I have to find some way of saying I will stop at some order in epsilon and then say that that's my best guess, right? And so people have actually found things at epsilon of 1 and 2, which are kind of in reasonable agreement with the numerical results or the experimental results. So that's not something that we're doing. Yeah. Correct. So again, here because of the nature of this, the way we've done this calculation, the way this calculation has been done is that we've kind of assumed that, I don't care about the microscopic lattice model. I have coarse grained, and I'm only talking about a Landau theory whose coefficients I have not calculated, right? But in principle, you could say, well, can I do this by calculating those coefficients, keeping higher order terms and some way and try to estimate TC? But really, the point of the Landau theory is, as the Bindu was saying, is not useful to calculate the value of the transition temperature. It's useful for certain things like, systematically doing these kinds of expansions, setting up field theory calculations to look at physics in the vicinity of critical points where there is some intrinsic length scale that's much larger than the lattice constant. So some kind of field theory approach is in fact valid, right? But it's not useful for microscopic numbers where you want to estimate TC for a particular model, which then depends on, oh, is it a triangular lattice or square lattice? Is it 2 dimensions, 3 dimensions, right? A lot of details. Is it first neighbor, second neighbor interactions? All of those will kind of matter at that level, okay? And none of those details are contained in this approach. Yeah. For which one? Oh, I see. If I stop here, you mean, and I set epsilon equal to 1 or something. Yeah, so here it does. I mean, these are like some simple, fractions that you can calculate. But of course, that's not true. Once you go to higher order, you'll get some things which don't necessarily look like. I mean, of course, if you terminate it at some order and set epsilon equal to 1, it'll look like some nice fraction. But you can think of that as some approximation to some thing which in general is not a simple fraction. So I think in 2 dimensions, there are completely different reasons for why these exponents actually are simple fractions. So beta, for example, is exactly 1/8, and it's not 0.125 something, right? But 2 dimensions is special, and it turns out that there are other reasons, like there's conformal invariance, some extra high symmetries in 2 dimensions at the critical point that allow you to actually figure out certain additional constraints on what these exponents are. But in 3 dimensions, for example, we don't have that kind of simple forms for the exponents. These are not simple rational numbers or simple fractions of the sort. They are in 2 dimensions. Okay. Any other questions? Okay. So with that, I mean, so this kind of brings us to, there were things which I was hoping to cover related to, other types of phase transitions, which, I don't have time to get into. So one of the things which I was going to talk about, which I'll kind of at least briefly mention, is, this idea that, this tells you that for any n, right, I will have a phase transition in 1 and 2 dimensions, so 2 and 3 dimensions, for example, right? And it turns out that, in fact, one thing that this epsilon expansion, does not capture is the idea that, when you talk about phase transitions involving order parameters of different symmetries, in fact, there might be, topological defects of the sort that I mentioned in the first lecture. So if you remember, in the first lecture, we had this picture of, if you have this nematic liquid crystals, we said that you can have disclinations where there are certain types of defects where the liquid crystal molecules basically kind of do something like this, where they wind around a certain point such that they execute half a rotation around a certain point defect, right? And these kinds of defects can also appear if you have, not just liquid crystals, but you can also write down these kinds of defects in, if you have just a spin model with 2 components. So if n is 2, then you can imagine that you can have, defects of the sort where the arrows around some point basically point all outward. Okay. And if you have such defects, clearly, if you try and calculate some correlations between spins, and this defect is some, imagine it's some thermally diffusing around, then the correlation between the spin at, let's say, this point and some point there will rapidly go to 0. Is this fine? Because if this defect is far away, then it will look like those spins are correlated. But if the defect kind of comes here, it looks like they're pointing exactly in the opposite direction, one pointing to the left, one pointing to the right. Okay. So if you have defects of this sort, you can have topological defects that can drive phase transitions. And that clearly is not captured by any perturbation theory that we did before, because we have no idea about these kinds of topological defects in this kind of epsilon expansion that we were doing before. Okay. And so it turns out that if you are in n equal to 2 and dimension, space dimensions 2, you can actually get phase transitions driven by the proliferation of these kinds of defects. Okay. And the most famous example is, and the first example, which is kind of extremely well studied, is this one, which was studied by Berezinski, Kosterlitz, and others. And what they argued for is that in fact there is a certain space of parameters which are somewhat similar to the flows that we talked about earlier, right? We should be talking about the flows of certain quantities under the renormalization group, but keeping track of the presence of vortices of the sort. Okay. And so now you can have a situation where I can have the analog of an inverse of the stiffness, and that's kind of the way people usually plot this. There is some coefficient, which is the coefficient that tells you how easy it is to bend this order parameter. Okay. And a second thing that they use to control this calculation, because epsilon, I can't use the epsilon expansion around 4 dimensions to do this. right? This is something very special to 2 dimensions. The fact that I have these point-like defects is very special to 2 dimensions. And so you have to directly work in 2 space dimensions. And now you have to come up with, is there some tuning parameter that will help me sort of control my calculation and let me decide, are there lots of these vortices or are there very few vortices? Okay. So they introduced kind of a second parameter, which is vortex fugacity, which, in effect counts, if, it essentially counts in some sense, it's like a number that tells me that if this fugacity is large, in some sense, I have a large number of these vortices. And if this fugacity is vanishing, then I have no vortices left in the system. And so I could do an expansion assuming that there is something that gives me a large energy cost for adding vortices to the system. So this is like an artificial parameter where if this parameter is very small, then I have very, very few vortices in my system. Okay. And now I can start asking under the renormalization, do these vortices, and not just vortices, but you also have the opposite of vortices, which are called anti-vortices. And the problem where an anti-vortex essentially is saying that, if I start my spin here and I go around in a clockwise, anti-clockwise loop, then the phase winds in this direction, in the, going from 0 to 2 pi. An anti-vortex would be that I take my loop in the same direction, but my order parameter winds in the opposite direction. So this one here would look, something like this. An anti-vortex would look something like this. Okay, it's not just flipping the arrows. That doesn't work, right? I actually have to have something where an anti-vortex, sorry, I'm kind of drawing this badly, but an anti-vortex is going to look something like that. Okay. And so what changes in sign between here and here is the gradient of the phase. So the gradient of the phase, if you think about a fluid or like a quantum fluid, you say the gradient of phase is like a current. Okay. And the current has to flip sign when you go from vortex to an anti-vortex. Okay. So these ones, you can think of these as vortices with charge -1 and vortices with charge +1. Okay. And if you have a very small vortex fugacity, it means that there is a dilute gas of plus and -1 vortices in the system and pretty much nothing else. Okay. And now if you coarse grain, okay, then these vortices and anti-vortices could meet. Imagine I take a bigger block, and I coarse grain, I might find that these vortices and anti-vortices effectively cancel off so that on this larger length scale, I see no vortices at all, right? And if I coarse grain, it's possible that this vortex number flows to 0, or the number of vortices or this vortex fugacity effectively flows to 0. Or you kind of keep doing this and maybe the number of vortices keeps growing in the system. Okay. And so it turns out that there are flows where you can get flows in this problem where which look kind of like this, where if you are at a very large stiffness, it costs a lot to bend the order parameter. If you allow for a small density of vortices, it costs a lot of energy. And when you coarse grain, the vortex fugacity goes to 0. So you end up finding no vortices in the system. Okay. And so this is one phase where this is like a no vortex phase or a vortex free phase in the problem. On the other hand, if your stiffness is a little weak to begin with, then you might find that in fact, the number of vortices just keep growing as you go to larger and larger length scales. Okay? So you'll get sort of a vortex proliferated. Phase. And so it turns out that this is a transition between something where topological defects don't exist at long length scales to one where topological defects are kind of liberated in the system in the problem. Okay. And a very crude way to kind of understand this, which is very useful, is to think in terms of just energy entropy competition, right? So if you think about the energy of a vortex, And if you just look at a picture of the sort, you'd be tempted to think that, oh, this looks like a point charge with an electric field that's kind of pointing radially outward. Okay. And so the electric, this will give us an energy. And that, that analogy is more precise than I'm making it out to be, right? It turns out that the energy for this vortex is going to be proportional to the how hard it is to bend this vortex, bend this phase. So it's going to be proportional to J, the spin exchange interaction, the J that we wrote down for the Ising model. We can write down a J for this spin, right? And it's going to be proportional to the logarithm of the size of the system with some suitable, there'll be some factor where A, let's say, is like a lattice constant. On the other hand, if you look at the entropy of the vortex, and okay, there are factors here which I'm not writing. There's some factors of 2 pi and so on, which I'm not writing. If on the other hand, you calculate the entropy of a vortex, right? You would say, well, the entropy of a vortex is, the configuration is fixed, but we will do the entropy counting the same way that we did for the kink in the 1D Ising model. Remember that kink, that soliton solution, we just kind of slid it around from one end to the other. It costed no energy at all, but it gave us an entropy that's related to the length of the system, right? Here, similarly, this vortex, let's assume that it's like a rigid structure of spins, but I can take the center of this thing and move it around. Okay. And if you do that, you would find that, oh, this gives me an entropy that's proportional to the log of the number of plaquettes, or kind of roughly proportional to the area of the system divided by some lattice constant set area. Right. So that's meant to be. So this is like the log of the number of configurations, right? And so this is going to go like 2 times the log of L over. And I think there's some factor of 2 pi. I forget what the factor, maybe it's 2 pi times G or pi times G. There's some factor here which I can fix later. So from here, you can kind of see that, I can now ask what is the free energy of a vortex? Exactly like what we did for the soliton solution in the 1D Ising case. We would say, oh, that's the energy of the vortex minus temperature times the entropy of this vortex. Okay. And now you find that if the temperature is very low, then the energy is dominant. Okay. And it turns out that both of these, okay, so the important thing is that both of these go like the logarithm of the system size. Okay. So if the temperature is very low, I would forget about this term. Right. And if you forget about this term, then clearly the vortex costs an infinite amount of energy in the thermodynamic limit. So you would say, I don't have vortices in my system. Okay. If, on the other hand, I reach a certain temperature, right, then both these things scale as a logarithm. So once I hit a temperature that's of the order of J, and again, there are some factors here which we can more or less work out with this estimate, then this will give me a vortex proliferated. This has no renormalization group in it, but it turns out that this calculation more or less, comes up with something like this, except this J is a parameter that depends on the scale. So here we are calling the stiffness to be some microscopic exchange coupling. But in general, this coupling is also going to flow with the length scale. So it turns out that you have to work out a little bit to kind of get what the TCs are, but the basic idea is that you get a flow equation that where the vortex fugacity flows to 0 on one side and it kind of basically blows up on the other side. And now there is like one last line that basically terminates here, and then everything else flows. So the log in the energy, I mean, it's really coming from, this one really comes from saying that the energy cost, E for the vortex, is going to be 1/2 times, this really comes from the twist energy between the spins at different places. And if I expand the cosine as, so really S dot S will look like a cosine interaction, but I can expand it for small angles. And so this would look like some gradient of the angle square integrated over space, right? And for a configuration of this sort, grad theta is set by saying that, gradient theta, when I integrate it over the perimeter, gives me 2 pi, right? So this quantity is just 1/2, or sorry, with a j by 2. So this quantity is really j by 2 times a 2-dimensional integral of grad theta, but grad theta is just 1 over r. So really grad theta dot dl, this closed loop integral gives me 2 pi, right? So grad theta is really 2 pi divided by 2 pi r. So that gives me 1 over r, which I have to square. And so this gives us the thing that this is, okay, we can work out this factor, right? So this is j over 2 times a factor of 2 pi coming from the angular integral, and then an integral over r dr over r square, and that's going to give us the logarithm. So it's pi, so it should be fine. So this goes like pi. So this is over some limit where the upper limit is the system size, and the lower limit is some ultraviolet cutoff, or like some kind of lattice spacing scale. So this gives me pi times j times log. So that's what. Sorry, that's what. Right. So in this case, that's right. So the logarithm depends on having both the certain, at the infrared, you're saying it's cut off by the length of the system. In the ultraviolet, there is some core, and I can't talk about this continuum kind of picture below some radius, right? But when you, sorry. Correct. So I have to cut it, right? Correct. Correct. And that I have to do provided I have like a single vortex, right? But what I can have, of course, I could take a finite L by L system, heat it up, and I could have single vortices popping into the system. If I have a system with periodic boundary conditions, then the total vorticity cannot change. And so you get a system where I start with 0 vortices, then I have to pop out like a plus and minus 1 vortex. And then I could pop out more and more of these plus minus 1 vortices. So you'll end up with a system which has an equal number of plus and minus vortices that can kind of move around and destroy your long range order. Or just the fact that they are, I mean, the dynamics is not important, just the fact that they can kind of pop in and out from the vacuum, as it were, will kind of destroy long range order at temperatures above a certain temperature or a stiffness scale. So this is really, the angle of temperature divided by G. Okay, so the charge of a vortex, I'm really calling Q to be the integral of dl dot grad theta, where theta is the angle that this arrow makes with respect to, let's say, the x-axis, right? And this quantity we've said is, sorry, this is some integer multiple of 2 pi. So if you want, you can kind of call Q to be, an integer charge plus or minus 1, plus or minus 2. Or of course, if there's no vortex, it's 0, right? And so you would have to, in general, sum over vortices with various charges, like, where the vortex could wind twice as fast, right? But it turns out that those vortices cost a lot more energy than vortices, clearly here, if I had a vortex with twice the charge, grad theta is twice as large. So this energy will go like Q square, where Q is the charge of the vortex. Okay. So if Q is big, it costs an energy that's much, much larger. Okay, so the leading order calculation that you do here, the small fugacity, is you even ignore vortices of higher charge You don't need to keep them. You just have a dilute gas of ±1 vortices, and that's enough to kind of give you this picture. So in some sense, this is the first example where you have some kind of idea that topology actually plays a role at a phase transition. And that was part of the, at least part of the reason that, certainly part of the reason for Thouless, but a large part of the reason for Kosteletz being awarded the Nobel Prize was really working out, the theory of, these kinds of phase transitions. And it turns out that this is broadly applicable to many, many systems, not just this XY model, but it turns out to be a broadly applicable. And the first time in some sense that these kinds of topologies started playing a role in the theory of phase transition. Correct. So for this one, it turns out that there is no local theory in these variables, right? Because the vortex is some highly non-local object. Okay, that's a good question, right? So you can't really write down some kind of a local theory in terms of these phase fields in the problem, okay? But it turns out that there is actually a dual description, or a description where you work in terms of other variables, where it looks like some kind of a local problem, okay? In some ways, imagine we did this Ising model example, just to go back, right? It's not really similar, but if you think of these kind of kink-like defects that we wrote down, right? You could work in terms of, you say, well, this spin field has some very complicated arrangement, the soliton-like arrangement, it's some very complicated arrangement. But by focusing on the kink itself, right, we realize that, oh, I can write down some theory in terms of kinks and, count the entropy and so on, right? So here, similarly, working in terms of the phase field or this field, the spin field, right? It looks like some extremely non-local object, right? But it turns out that, once you start thinking in terms of point charges, which are kind of, you can think of these as analogs of electric fields. Really, you have to think of the gradient of theta as like the analog of an electric field. And you can then view this as some kind of a Gauss's law almost, right? So there's really a line integral and not. So this doesn't look like E dot a normal. This looks like I'm kind of taking a parallel component and integrating it, right? But if you define a field that is a cross product of the spin field with the Z component, which is just pointing out of the board, then this just rotates this vector here. And you can rewrite this line integral really as, it rotates everything. So what you get is something that looks very much like E dot ds, okay? And then this topological charge really looks like an electric charge in that description, okay? And so you can write down a theory of charges interacting through some logarithmic interactions, and there are ways to go from there to the theory that looks kind of local. So these are what people call Sine-Gordon field theory. So there are ways to kind of dualize from here to a description that is not in terms of these spin fields or these phi fields. Well, I didn't write down the phi fields, I suppose, but okay, we did the calculation here in terms of these angles, but rather than working in terms of these angle fields defined at all points, right? We can work in terms of certain dual degrees of freedom where the theory kind of looks local in some sense. Right. Right. Correct, correct. So I know that, I have to have some like an, some number of the number of kings minus the number of anti-kings is going to be, some is 1 or some odd number. Correct. Correct. Right. So in principle, even here, if I were to kind of work, with a boundary where I force the spins at the boundary to take on a certain texture, then I would be forcing that the number of vortices minus the number of anti-vortices must take on some particular values, which will be like the charge, total charge in some sense contained within this region. So yeah, so even that looks like a Coulomb-like problem where, I can take something at the boundary and do E dot ds, and I learn about what is the total charge. Similarly, here you can do this the same thing with vortices, vortex configurations. All right. So I don't know if maybe should I stop here, or I just wanted to maybe at least can I take a few minutes? So the last thing I wanted to mention, which again, this we kind of had this very brief discussion. But the other thing that I wanted to cover, which I did not, was really thinking about what happens to these kinds of phase transitions when quantum mechanics plays an important role. Okay, and there we have to actually worry about sort of not just fluctuations in space, like we are doing, where you're saying we are defining some correlation length, and we are talking about correlations between spins at different points in space. We also have to think about, what causes these phase transitions may not be the same. In this case, for example, the phase transitions, everything that we talked about was, taking a phase transition where you're heating the system up or changing temperature and going through some phase transition, right? But there are examples where you could take, two different, let's say, terms in a Hamiltonian which don't commute. Okay. And the simplest example of something like that is, an Ising model. But instead of thinking of a classical Ising model, we can write down sort of a quantum Ising. And what this means is now that I'm going to write down some operator for the Hamiltonian, and this operator, one piece of it looks, let's say I do this in one dimension, one piece of it looks exactly like the classical problem that we wrote down, except now instead of these being plus or minus one, which were, we were thinking of some eigenvalues or some numbers earlier, here I really think of these as Pauli matrices, as operators, the SZ operators, right? But now with this, I can write down terms which, so if this was the only problem, right, then I could have said, well, I can just work in terms of the eigenvalues of sigma z, because everything commutes with everything else. I can just rewrite this problem in terms of eigenvalues of this operator, and I can sort of try and solve this problem exactly like a classical problem, right? But that doesn't work if you have terms which do not commute with these things here. So in particular, I could write down, and the simplest one of these is I can write down a term like this, which is like a magnetic field, except it's not pointing along the z direction, but pointing along a transverse direction, where x and z don't commute. In fact, these Pauli matrices, at the same site will anti-commute rather than commute, right? And of course, they square to 1 and so on. These are just identities, right? And now it turns out that as you tune these numbers in a Hamiltonian with no mention of the temperature, we could get transitions where, as I tune this parameter, this dimensionless parameter, I could go from a state where when H is 0, this looks like an Ising model, and let's say I'm at 0 temperature. So I'm really talking about the many-body ground state of this problem, has a broken symmetry because sigma z will want to be all +1 or all -1, right? So the ground states are, something like this, when H is 0 or very close to 0. Okay. But when I turn on a magnetic field, you'd see that, okay, I can start, what this does is going to flip spins. Sigma x acting on a spin up will flip it, right? And then operators of this sort can actually take that spin down and kind of move it along the chain. Okay, so a pair of sigma z's, so if I act sigma z on a state which looks like up, down next to each other. What did I want? No, I can have this, sorry, in this case, I don't have plus minus terms here, right? So if I'm in this basis, you can sort of start nucleating spin flips in this problem. Okay? And if you start nucleating spin flips, you can basically write down, something that's a linear combination that wants to be a linear combination of up and down, is going to be induced by H in perturbation theory. And what you find is that you can essentially take this, ordered state, and instead of pointing in the Z direction, it will develop a little bit of a component along the X direction. Okay. But then eventually at some point, you find that the spins have no tendency to point in the plus or minus Z direction at all. In other words, at some point, you go from a state where sigma iz is non-zero to a phase where sigma iz is in fact zero. Okay. And so this marks sort of an example of, a quantum critical point where you are at zero temperature, and it's really the physics of the fact that these operators don't commute with each other that leads to a transition from one type of state to another type of state. Okay. And so there's a whole rich field of kind of trying to understand, these kinds of zero temperature phase transitions between different states, and, what it means, for example, if I turn on temperature, then, what are the manifestations of this at finite temperature, which any real experiment, for example, would be sitting at finite temperature. So what is the nature of this transition? Can one use some kind of renormalization group theories to understand this? And what is its kind of effects at finite temperature? And now we have to start thinking about not just correlations in space, but also correlations in time. You make a certain fluctuation, and at a later time, there might be some fluctuation that shows up somewhere else. Right? And so there's this whole field of quantum phase transition. And I was hoping to at least do a little bit of it, but given time, and it's not really possible. So what I'll do is, I've posted some notes, some lecture notes, which Sanjeev said can be posted on the same website. But at least I'll have like a little bit more of this on the last lecture. I'll just put a little bit of notes on this, but nothing. So anyway, so that brings us to basically the end of this thing. So if people have questions, we can kind of discuss them. Yeah.
So these lectures, the notes are already available. So if you have seen the website, there's a link in the front page, right? So it's linked there. Yes.
And okay, if you have any further question, you can just ask him.
I have some just slightly broad questions. One is, one often hears with the critical points and critical behavior that you have to have infinite degrees of freedom. There's sort of this myth that finite systems do not exhibit phase transitions. So I wanted to know, from a very practical point of view, in all of these cases, you do have lattice cutoffs and so on. So, and it's true that as you increase the size of the system, the sharpness of phase transitions becomes more evident, so on. I was wondering if there is a, deeper understanding of whether this is simply a limit of the theory, or whether even in the finite case, one really thinks of it as phase transitions. For example, that quantum critical point, it's a finite system, a finite set of spins, but you can still describe things that happen at that point. And
Right. So in fact, one thing that people do, and this is true certainly, for example, in numerics, where you can't really study, unlike an experiment, you're not dealing with a very large number of degrees of freedom in like typical numerical simulations even, right? And so what people have to do then is to say that, I have to have some theory of, finite size scaling. In other words, I have to ask, if I measure a certain property in a finite system, and I take the length of my system and I double it, right? But let's say I calculate, the correlation between 2 points, but I just keep doubling the size of my system, then eventually this correlation will kind of saturate and become independent of what the system size is, right? So what you expect is that you would get some kind of scaling of quantities like correlation functions, and it will depend on the ratio of the length of the system to the characteristic length that's important near a phase transition, which is the correlation length. Okay. So what people often do is to ask, well, can I write down some, correlation function? And maybe what it does is, I can write it down just like we wrote down how things scale, as you tune your magnetic field and you kind of go to larger and larger length scales and you're asking how these things change. Similarly, you could kind of look at some fixed correlation length and ask how things change as a function of L or vice versa, fix some large system size. And if you come closer and closer to the critical point, this denominator will diverge. And so people can write down sort of this theory of, again, this is not something that we discussed at all, but there is some theory of, finite size scaling at phase transitions, where you want to be able to kind of determine the nature of the transition without necessarily having access to a truly thermodynamic the number of degrees of freedom. Right? And this one has to do now, if you do, this is kind of in a classical case where you have to kind of do this kind of scaling. In the quantum case, you have to do something where, you have to do this not just in space, but also in the time direction, right? So you have to introduce some notion of a spatial correlation length psi, but there is also a correlation length along the time direction. And in general, there is no relation between these two, right? Because they won't even have the same dimension because this is some, time interval, this is some space interval, right? And unless you have a theory that happens to be, like a relativistic theory where, you expect these two might be proportional to each other, right? In general, these two will not be directly linked to each other. They will be linked through some, some prefactor times some length scale to some power. Okay. And this power is, one additional thing that becomes important at quantum phase transition. So it's something called the dynamical critical exponent. And now one has to do finite size scaling. If you try and do a quantum mechanical problem, you can rewrite it, and this is not something that I discussed, but you can rewrite it as an effective sort of thing that has both space and time degrees of freedom. And you have to do finite size scaling both in the space direction, but also in the time direction. Yeah.
And then one I track like this, this time lapse. So, for example, in the Ising model, we have this anisotropy Ising model, and I think that's why because of this anisotropy, these two this correlation length will depend on the scale, and because the scales are different in both directions, so there is no clear relation between the correlation lengths of these.
Correct.
Now, if I figure out that the Z, which is the relation between these correlation lengths, is some value, does that, for me, does that sort of cement that there is some phase transition, or can there still be phase transition?
So the fact that there is a diverging length scale at a problem, right? So are you asking whether this only happens at zero temperature? So for example, in this case, right, if I went somewhere here, but at some small non-zero temperature, you would find length scales that appear to blow up and time scales that appear to blow up, but they will not quite diverge because you're at non-zero temperature. Right. In cases, I mean, there are cases like this where at finite temperature, there may be no phase transition at all. you could get the length scales and time scales appearing to diverge, but eventually they saturate at some point. But that's not what you're asking. You're asking, can I get something where the time correlations look like they diverge, but not the space correlations? Is that?
Yeah.
Right. So this is actually so this is a problem which people have been thinking about for a while, right? So you can ask, is there some version of, so this, so this is an example where I might say, I have some quantum critical point where I have diverging length scales and diverging time scales. So the system develops some kind of long range ordered phase, and this would be, some version of a classical transition, except, with this time fluctuations included, right? Quantum fluctuation. You could also ask, well, can I get something where there is no diverging length scale, but only some kind of diverging time scale? So can I get phase transitions where, people kind of call these, they call like versions of, can I get some version of local criticality? Can I get something where if I look at correlations in the time direction, it has power law, but correlations in the space direction look like they're very short ranged? So these are things people are thinking about, I think, motivated by some experiments. And there is some examples of this that people have kind of found where correlations in the spatial direction might be very short ranged, but correlations in the temporal directions are relatively long ranged. Right. You could also think of, for example, so things like the Kondo problem, right? Where you might say, well, imagine I have a single spin impurity coupled to some gas of electrons, right? And I can ask, well, if I integrate out, sorry, I'm kind of jumping a bit, but if I imagine integrating out the electrons and I can write down the spin, it is completely just situated at one point in space, right? And so there's only a time axis, there is no space axis, right? And so this would be an example where, I can have correlations in time for something that has no spatial degrees of freedom at all, right? And so people are asking, is there a version of this where I have a lattice of spins? Can this still happen? Or do I necessarily have to have long range spatial correlation? So there is people thinking about these kind of Kondo lattice problems where this kind of questions have been thought about a bit, but I don't know whether there's any convincing. Yeah. Correct.
Whether those are still related by the same shade or that is different. When I still have a dynamic, I can still define a dynamic electron and away from the physical part.
Correct. But these quantities are defined of, the psi is defined. Correct. Same?
I mean, it doesn't, I mean, at the critical point or away from the system, they're just the same way, right?
Correct. So the assumption is that, these two, the length scale and the time scale are related, where if I'm going slightly away from critical point, then both these are finite but large, and they are related by this exponent.
Yeah.
So, no, I'm thinking like some of these discussions are going on, like important and becomes important. So, are you considering also
Yeah. So correct. So the simple cases are ones where you can think of this as a problem where, okay, so I didn't get into this, but you can kind of rewrite this problem as if it's like an Ising model, which has both space and time labels, right? And so you would have some kind of one-dimensional lattice of spins, but I have like copies of it at different values in my Euclidean imaginary time. And if you do that, then you can do the renormalization more or less the same way, right? For certain things, right? But if you're at finite temperature, for example, it'll look like, and this is again not evident from anything I've done, it'll look like there is a cutoff in the Euclidean time direction because my fields have to be periodic in the imaginary time direction. And then it'll look like a problem which is in d dimensions, space dimensions, it could be infinite, but in the time direction, it becomes a finite slab, right? And so then you can certainly calculate things in Euclidean space, but then the question becomes how to kind of infer anything about real time correlation. Right. So that's provided Z is 1, then I can kind of rotate from space to time, and both these give you similar correlations. Yeah. Yeah. Right. But if Z is not 1, then you kind of have to do the scaling differently. So your Landau theory would have terms of this sort, right? So there'll be some time scaling of my field. And there'll be in general some spatial, let me write some lag. Right. So this will tell you that, space and time look like they come on equal footing, because if I change my time scale by a factor of 2, space by a factor of 2, then this overall thing, changes by some factor. But you could also have theories which look like this, where space and time come on a footing that's not equivalent, right? And so if you change space by a factor of 2, time scales will change by a factor of 4, right? So this would be an example where Z is 2. But again, you can kind of ask, is there a way to do this renormalization group? And now you have to introduce one additional exponent, which tells me, how the space and time correlations are kind of related to each other, which is basically this additional factor of this additional dynamical critical exponent. So this would be an example where, I would think of Z as 2 because spatial scales go like the square of the, sorry, time scales go like the square of the spatial length scales. Oh, no, so I think these are examples of, I think, what people call like Lifshitz theories. I think where, that's one example where Z is 2. Oh, what do you mean? What is the RG called? Oh, is there a name for that? I don't know. I think you can I think there's like renormalization group near quantum critical points, but I don't know if. So one thing which, yeah, so in many of these cases, you can map them onto some effective anisotropic classical problem. So the RG looks very similar to some anisotropic classical problem, right? But not for all quantities, and certainly there are cases where quantum mechanics plays a more important role than just changing dimension. So you could have a system where in quantum mechanics, the action need, when you write down the path integral, the action need not be real, right? And so you could have something where I have some complex numbers in the action and they might play a role. And so these kinds of, so the simplest examples are things like, Berry phases can play a role at certain phase transitions. Yeah, so you can kind of do RG just along the time direction for that problem, right? So it takes the form of some kind of, Ising-like model with some long-range interactions and so on in the time direction. So there is some, non-local, correct, it's only time. And then in the time direction, probably this answers sort of the other question that was asked. In the time direction, the interaction need not be local in time. Right, so you can get some highly non-local and time interactions, and when you do the RG for that, you can get some non-trivial answers because of that fact that it's like some long-range interacting. Yeah.
Either have all spin up or all spin down, but I could also have a linear combination of those as being the ground state. And if that linear combination happens to be such that their coefficients are the same, and it seems like there is no symmetry that is broken because.
Correct. That's similar to the case where, you do this in the classical problem, right? So in the classical problem, you would say, well, I could have an ensemble where I take all up and all down, and they clearly have the same probability. And so if I sample both of them, I will not see a broken symmetry, right? So in the classical case, the way you get around this, right, is to say that, I'm going to start in one state.
There's a barrier then, like.
Correct. Then you say, oh, there is a free energy barrier to go from, let's say, all up to all down, right? Now we would say the same thing, except now we would say, oh, well, here I'm not talking about a trying to classically kind of climb over this barrier, right? I can basically tunnel through, right? And I can write down my ground state wave function as some linear combination of, up, let's say 1 over root 2, up plus down, right? But I could also write down a linear combination, which is anti-symmetric, right? And now the claim would be that, these two configurations will have some, will be degenerate, right? But in the presence of a small non-zero H, these states that I find psi plus and psi minus will have a very, very small energy splitting between them, right? So this is like, you go from all up to all down, right? But using local operators of this sort, right? So imagine I start here, then the way I'm going to get there is by acting with H, as many times as there are lattice sites, right? So you would expect that the splitting E delta E, right, will be exponential simply because, I'm trying to do perturbation theory in H. Each time I want to do this, I'm paying some cost. And so this thing is going to go like some exponential of n times some number. Okay. And so this will be proportional to, H and maybe H over G or some numbers will be coming here, which I'm not writing down. But basically it's like H over J to the power of n. I have to go to some nth order perturbation theory where n is a number of spins in order to connect from here to there, right? And so you would expect that, I can write that, H over J to the power of n is like some, some number here, right? I can write down some function of H over J here, right? Let me really write it like this. Crudely, right? So now you would expect that now I can do the following. I can do the analog of this experiment, right? I can say, imagine I start off in the all up state, right? And I can ask, how long will it take me to land in the other state, right? And now you'd say, well, it's like a two-level system. The splitting is extremely small, right? So I can write down some effective, two-level problem where, my all up state is here, all down state is there, right? Sorry, let me, all up state is there, all down state is here, right? These diagonal energies are exactly the same, but I have some H over J to the power of n that tries to mix them, right? And the same thing here, same thing here, right? And so if you start here, it's going to take you an exponentially long time in order to go from here to there by this kind of tunneling process. Okay. So again, you have to take this limit where you would say, well, I have to take the limit where I imagine starting off in this state, taking the thermodynamic limit, then it will take me an infinite amount of time to actually go to the other state. Right. So all we've done is replace, our thermal averaging of over these two, which we could say, I can bias it in the beginning, and then there is a huge barrier to kind of overcome where this barrier scales with the size of the system. Or in the quantum case, we want to tunnel through, but for the same reason, this tunneling barrier is huge because these two configurations are very far away in terms of any local things that I can do. So what you get is an effective two-level problem. If you start here, it'll take you forever, an infinite amount of time to switch. This one? Oh no, this is just doing perturbation theory in this one, right? So to first order in perturbation theory, I can flip one spin. If I do second order, I can flip two and so on. So I have to go to nth order perturbation theory before I can flip all in. Roughly, that's the counting. Yeah. All right, so thank you.